It seems like everything is going green these days. But there's one mode of transportation that seems to be clinging to the traditional fuel-loving ways. And while commercial aviation has made strides through smarter design and cleaner engines, many of those gains have been nullified by more air traffic.
The challenge is enormous. This is a large industry. It will take decades to convert. The good news is that we will have a solution as early as 3 years out that people can get into and start moving zero emission.
And it turns out that the solution could be all around us.
Hydrogen is the most abundant element in the universe. And so if you had to use something, it would be great. The only product of the chemical reaction between hydrogen and oxygen is water.
We looked at the fundamentals of what it would require to take an aircraft up in the air of significant size over significant distance, commercially relevant. You get to hydrogen fuel cell being the best approach from the cost of fuel, efficiency of utilization of the fuel, and the mitigation of the climate effects.
Serial clean tech entrepreneur Val Miftakhov started ZeroAvia following his previous success in the EV charging industry.
So the beauty about hydrogen in general is that the energy density of hydrogen as fuel is actually 3 times better than jet fuel. So you can see any size of aircraft going for any distance that jet fuel aircraft can go over time, right? It will just take a significant amount of time to get the industry over, but this technology can scale to all sizes of aircraft that we use in commercial service.
ZeroAvia uses a hydrogen fuel cell to produce electricity to turn a propeller. Unlike a traditional engine which uses combustion to create energy, a fuel cell generates electricity through an electrochemical reaction. In this case, hydrogen and oxygen are combined to generate electricity, heat, and water. ZeroAvia has flown a 6-seater aircraft on a hydrogen fuel cell, a world first. Now they're aiming bigger, at 20 seats. That's technically commercial.
One side of the aircraft, the left side, we replace the engine with our power plant. We still got the normal engine on the right side. And part of this is, in aviation, you want to ramp up a risk profile in meaningful steps. So anything happens, we have the second engine. But even in the first flight test campaign, what we're planning to do is to demonstrate operation of this aircraft purely on zero emission power. On the left side engine, once we take off, we're able to switch over to completely zero emission power. Hydrogen is used throughout all sections of a flight. That maximizes the efficiency of the entire operation. That reduces the weight, provides for best sort of mission capabilities, payload and range.
Building power plants and fuel cells is one thing. Creating a whole new infrastructure for supplying hydrogen is something entirely different.
In automotive, a big part of the reason why hydrogen did not take off is because the fueling infrastructure needs to be so distributed. Let's say in the United States, you have 100,000 fueling stations. Compare that with aviation, where 95% or more traffic in the United States is concentrated in 100 locations, right? So that's a 3-order magnitude difference, which makes build out of the infrastructure much simpler. It's much larger, much more concentrated stations, but they're much fewer in quantity.
Calling it simpler might be underselling the challenge of distributing hydrogen, which, unlike other fuels that can be easily transported in liquid form, is usually found instead in a gaseous state.
How do you get the hydrogen from point A to point B? We don't have pipelines for moving hydrogen around. We don't have all the specialized trucks to move them around. And so we got thinking we need a solution that can be a low capital expenditure solution. And that's the genesis of the company.
John Paul Clark is the co-founder and chief innovation officer of Universal Hydrogen, a startup that has designed a modular tank system for the domestic turboprop market. Like ZeroAvia, it allows for retrofitting planes already in use.
Each module has 2 capsules, and so what we do is load it into the aircraft as if it was cargo, strap it down, connect it to the aircraft, close the loading door, and that would be it. When you get to your destination, you'd basically unload it, put it back in a truck, send it back to the production site to get refilled. We needed to basically come up with something that could both fit in containers and also fit in the aircraft, not require increases in the maximum takeoff weight of the aircraft.
This compromise is one of the biggest hurdles that may prevent widespread adoption of hydrogen.
Obviously, you're going to have to take out some seats because the energy density of hydrogen is less than jet fuel, and you can't store it in the wings practically, so you're going to have to take away some space in the fuselage.
In the ultra-fine margins of aviation, removing 10 to 20% of your seats is a tough ask. But that hasn't deterred startups like ZeroAvia or Universal Hydrogen.
The maintenance cost of a fuel cell motor system goes down, and it goes down significantly, because motors and fuel cells have much fewer moving parts than a gas turbine engine. And so the wear and tear is much lower, and therefore the time between overhaul is longer. And so when you put all that together, our numbers indicate that the CASM, cost per available seat mile, actually goes down slightly or is at the worst equivalent to what you have now. So what you will have is a smaller cabin, a smaller number of seats. However, the cost for each of those seats to operate it is the same or better with the hydrogen.
Like ZeroAvia, Universal Hydrogen is also working on engines, successfully testing their 2-megawatt Ironbird that will allow them to retrofit planes carrying up to 55 passengers. ZeroAvia is aiming for their first commercial hydrogen electric flight between London and Rotterdam with their 19-seater by around 2024. But much like the range anxiety that has plagued some battery-powered electric vehicles on land, hydrogen fuel cells are also fairly limited. At this point, they still don't have the capacity to power a common 100-passenger jet. Beyond fuel cells, however, there is another hope for our lightest, most abundant element: burning it.
The first eureka moment, I suppose, is when we saw steam in the exhaust, because we were thinking to ourselves, we're burning something here when we're producing absolutely no CO2.
An expert in gas turbine combustion, Professor Bobby Satie leads research at Cranfield University in the UK. Built on a former RAF base, the college runs multiple aeronautical programs. But what Bobby is focused on is burning hydrogen as cleanly as possible.
So what we're trying to demonstrate in this rig is how we can conceive some hydrogen combustion technologies that can be integrated in the next generation aircraft engines, which will deliver not only zero CO2 emissions, but also ultra-low NOx emissions.
NOx, or nitrogen oxides, are a significant source of air pollution globally. They're the dirty particulates that cause smog in cities, usually spat out by diesel cars, scooters, and buses.
Hydrogen is characterized by much wider flammability limits, which means we can go to much leaner combustion, and as a result we can burn at much lower flame temperatures, and that's better for reducing NOx emissions.
Going leaner means burning fuel with an excess of air in the engine. Using something like gasoline, lean burn emits far fewer hydrocarbons. Doing it with hydrogen also delivers cleaner emissions. While NOx is a pollutant, hydrogen combustion produces up to 90% less nitrogen oxide than kerosene. So while burning hydrogen isn't technically as clean as using it inside a fuel cell, it's still a huge improvement over jet fuel. Unfortunately, like any radically new idea, there are other potential byproducts of the process that aren't fully yet understood.
NOx is clearly one of the main emissions we need to consider, but the aviation community is also asking themselves, and the community in general, what about all the water vapor emissions? And some studies have shown, albeit there's still a large degree of uncertainty about it, that contrails and cirrus clouds that may be induced from contrails could contribute to global warming about 4 times the amount than CO2 does. We know that if we are going to be burning hydrogen, we are going to produce a much larger amount of water vapor emissions. And if we are going to be producing a much larger amount of water vapor emissions, then the propensity for contrail formation is also going to increase.
In spite of all these challenges, hydrogen is being taken seriously by the broader industry. Companies like Universal Hydrogen and ZeroAvia are gaining the attention of investors looking for viable and eventually profitable solutions. Industry giant Airbus wants to introduce a hydrogen-powered passenger aircraft by 2035, recently announcing plans to retrofit a gas-guzzling Super Jumbo with a hydrogen-burning engine. The modified aircraft will add a 5th engine, adapted for hydrogen, and will be mounted on the rear fuselage. The A380 is the largest passenger aircraft in existence, so it offers plenty of room to store the 400 kilograms of hydrogen. The company's designs for a blended wing concept to store extra hydrogen also offer a glimpse of our flying future. Apart from the complex engineering challenges faced by airplane manufacturers, there are also difficulties in production of hydrogen itself. Nowadays, most of the hydrogen used in fuel is derived by splitting it off from molecules of natural gas. But that requires a good deal of energy and also produces carbon dioxide. To make green hydrogen, the electricity used to run the electrolyzer must come from a renewable resource, which is currently a lot more expensive. As with any new technology, however, initial costs are daunting, but time may be the best remedy here.
If you look at economics of hydrogen fuel production, for example, versus fossil fuels, for instance, the cost of hydrogen is all based on capital expense and very little operating expense. It's sort of similar to solar power, right? You put solar panels out there and they produce power for 20-25 years. The operating expense is relatively low. What that means is that as scale grows, as we've seen with the solar panels, the cost of output drops dramatically.
So the first phase is not about the most efficient aircraft. It's not about the aircraft that will deliver the lowest NOx emissions. It's about demonstrating that we can carry hydrogen safely on board, we can burn it safely on board, and it can be used to fly a passenger aircraft. The key thing is that we don't try to put everything in the first generation, or we're just going to delay the entry into service. So to try and keep it as simple as possible.
If there are some questions on the margin, they're all in the sort of business model and market adoption realm. It is very hard to create a technological argument, or impossible to create a technological argument that says, well, it's not going to work, right? It is going to work.